Good day everyone, I'm Loveless Bulasser. Today I will report about subgroups, the continuation report of Miss Lovely Joy Saludo. So let us show. Okay. Definition 4.1.7, let G be a group and S be a subset of G. Let S is equal to S divides H is a subgroup of G and S is a subset of H. Define intersection of H is an element of S to the power of H. Subgroup generated by S is the intersection of all subgroups S of G such that is S is subset of H. Then the subgroup generated by S of G is called the subgroup generated by S. If G is equal to subgroup generated by S, then S is called a set of generators for G. Let's continue. Wait for a while. Okay, let's continue. If either S is equal to non-empty set or S is equal to element A, then the subgroup generators by S is equal to element A. Also, the subgroup of G is generated by G is equal to G. We now proceed to obtain a characterization of a subgroup generated by a non-empty subset in terms of the elements of the group. Let S equal to H divides H is subgroup of G and S is a subset of H, where S is not equal to empty set. Then S is less than or equal is a partially ordered set where less than or equal denotes the set inclusion relation. In this set, the subgroup generated by S is the last element. Hence, the subgroup generated by S is the smallest subgroup of G which contains S. Since the subgroup generated by S is a subgroup of G, we must have for any S sub 1, we have S sub n is an element of S, the product S sub 1 is the power of E sub 1, S sub n to the power of E sub n is an element of the subgroup generated by S, where E sub I is equal to positive and negative 1 for I is equal to 1, 2, and n. Thus, if A denotes the set E sub 1 to the power of E sub 1, S sub n to the power of E sub n divides E sub I is an element of S, E sub I is equal to positive and negative 1 is equal I is equal to 1, 2, continuation, then n, and therefore n is equal to 1, 2 element. Then E is subset of the subgroup generated by S. Note that if S is an element of S, then E is equal to 88 to the power of negative 1 element of A. In the following theorem, we show that E is equal to the subgroup generated by S. Therefore, S does generate the subgroup generated by S in the sense of multiplying elements of S or their inverses together to build up the smallest subgroup containing S. Let's proceed. Okay, let's proceed. In theorem 4.1.8, let S be a non-empty subset of a group G. Then the subgroup generated by S is equal to E sub 1 is to the power of E sub 1. We have E sub n to the power of E sub n divides E sub I is an element of S. E sub I is equal to positive negative 1, I is equal to 1, 2, continuation, then n is equal to 1, 2, continuation, and an element. Proof, let E is equal to E sub I, E sub 1 rather, is to the power of E sub I, E sub 1. S sub n to the power of E sub n divides E sub I is an element of S. E sub I is equal to positive and negative 1. I is equal to 1, 2, continuation n. Then n is equal to 1, 2. We have already noted that E is subset of the subgroup generated by S. We show that the subgroup generated by S is subset of A by showing that E is a subgroup of G containing S. Recall that the subgroup generated by S is the smallest subgroup of G containing S. Let S is an element of S, then S is equal okay. Then S is equal to is to the power of 1 is an element of A, and so S is a subset of A. Let S sub 1 to the power of F sub 1, S sub M to the power of F sub M, T sub 1 to the power of Q sub 1. Continue. T sub Q to the power of G sub Q is an element of A. Then is sub 1 to the power of F sub 1, then S sub M to the power of F sub M. T times T sub 1 to the power of G sub 1, then T sub Q to the power of G sub Q. The power of negative 1 is equal to E sub 1 the power of F sub 1, then S sub M the power of F sub M, T sub Q the power of negative G sub Q. T sub 1 the power of negative G sub 1 is an element of A. Thus, A is a subgroup of G by theorem 4.1.3. Hence, the subgroup generated by S is a subset of A. So, the symbol in this, the black, kanina na black dire, so it is called end proof based on the book that I found. Charot. For E is an element of G, we use the notation the subgroup generated by E rather than the subgroup generated by E is an element to denote the subgroup of G generated by element of A. Okay. And proof by theorem 4.1.8, we have the subgroup generated by A is equal to E to the power of E sub 1, then E the power of E sub M divides E sub I is equal to positive and negative 1. I is equal to 1, 2, then M continuation, M is equal to 1, 2 element. Okay, next is equal to, the answer is equal to E sub E to the power of E sub 1 plus E plus the power of E sub M divides E sub I is equal to positive and negative 1. I is equal to 1, 2, continuation M. Therefore, M is equal to 1, 2 element is equal to E sub N, E to the power of N divides in is an element of Z. Is an element of integer, positive integer rather. And then again, as what I told last, this black kanina na black dra, it is called end proof na niya sa corollary 4.1.9. In notation, we should have the subgroup generated by A is equal to NA divides N is an element of integers. Let N is greater than or equal 3. In chapter 3, we prove that every element of E sub n is a product of 3 cycles. Theorem 3.123. In the following theorem, we conclude that E sub n is generated by the set of all 3 cycles. Okay. Theorem 4.1.10. Let n is greater than or equal 3. Then E sub n is generated by the set of all 3 cycles. In 4.1 subgroups, prove that since 3 cycles is an even permutation, every 3 cycles is an E sub n. By Theorem 3.1.23, every element of E sub n is a product of 3 cycles. Hence, E sub n is generated by the set of all 3 cycles. This is the end proof. We now turn our attention to the product of subgroups. Okay, in theorem definition 4.1.11, let H and K be non-empty subsets of a group G. The product of H and K is defined to be the set. Okay, HK is equal to HK divides E is an element of H, K is an element of K, small k. Let H sub 1, H sub 2, continuation H sub n be non-empty subsets of a group G. We define the product H sub 1, H sub 2, continuation H sub n of H sub 1, H sub 2, then continuation H sub n to be the set. H sub 1, H sub 2, H sub n is equal to H sub 1, H sub 2, H sub n divides H sub I is an element of H sub I, is therefore I is equal to 1, 2, continuation, then n element. Okay. In 4.1.12 example, consider the group of symmetries of the square. Let H is equal to R360 D sub 1 and K is equal to R sub 360 H. Then H and K are subgroups of G. Now H of HK is equal to 360, 360, then R360, then R360H, then D sub 1, R360, then D sub 1H is equal to R360H, then D sub 1, R90. Since it's D sub 1 is equal to R270 is not does not belong to HK, each of K is not closed under the binary operation. Hence, HK is not a subgroup of the symmetries of the square. Also note that KH is equal to R60, R60, R sub 360, D sub 1, HR sub 360, HD sub 1 is equal to R 360, D sub 1, HR 270 element. And H union K is equal to R360, R390, R180, R270, H, V, D sub 1, D sub 2 element. In example 4.1.12 shows that in general, the product of subgroups need not be a subgroup. In the following theorem, we give a necessary and sufficient condition for the product of subgroups to be a subgroup. Okay, that's all for today. And this will come to our next reporter, Miss Nudilin Rosiliosa, for the continuation of the report. Thanks for listening and God bless everyone. Thank you, sir, and thank you, classmates, for listening. Thank you.